All right, 6.5, force and pressure. So now we're going to talk about how those things are related. So we've been talking about force. We've been talking about how that creates acceleration. Now we're going to add in a little bit more. And notice that we're using A, but this is a different A here. This is a capital A. So we're talking about area. So force, and that's still equal to mass times acceleration here, divided by the area gives me the pressure. So, you know, if I apply a certain amount of force to that area, or a certain amount of force to this area, you know, my pressure is going to be different. So the pressure is the force divided by the area. If I apply the same force to both of these, since this one has much more area to it, the pressure would be smaller because I'm dividing by pressure here. So I wouldn't have as much pressure in that area. When we measure pressure, we talk about it in terms of pascals. So it's force in newtons per square meter. That's a pascal. That's not a very big term. Pascals are really, really small. You know, think about when we're talking about a newton. A newton is not a big force amount. You know, it takes, you know, for a kilogram, it takes about 10 newtons. And so if you take that pressure and spread it out over 1 square meter, that's not very much. So pascals are a pretty small term. In fact, most of the time when they're talking about pressure, it ends up being kilopascals that they talk about because pascals are usually pretty small. Take a look at these two physics books here. Notice they're both sitting on the table. They both have the same mass, so their mass is the same. So therefore, they're applying the same amount of force to the table. But the one that's laying down, that force is spread out over that whole area. The other one is spread out in a smaller area. So the pressure on the one standing up is greater. So we've got a lot greater pressure on that one than on the one that's laying down, because the area that it's applying it to is a lot smaller. So, you know, if you're standing on 2 feet and then you pick up one of your feet, you are now applying more pressure to that surface area, you know, when you're walking through it. People who wear high heels, if they have those small, you know, really small heels on the back, that applies a lot of pressure versus a shoe that's very just flat, and you break that area up, or it's a lot bigger area. So, you know, pressure all depends on the area that you're applying that force to. So here's an example of, you know, this is the author doing this example, and I'm sure that someday we'll get to see Sean, you know, laying down here, and we'll, you know, break the brick on top of him, and it'll look beautiful. But, you know, the reason that this doesn't hurt him is because all of these nails, I mean, I can't remember how many they put in there, but there's a lot. Well, all of that pressure is divided up between each of those nails. Now, you do the same thing with one nail, and that thing's going right through him. You know, or even probably 5 or 10 nails is going right through him. But you do it with 1,000 nails, and this whole thing is, you know, it is split up. The pressure is not all in one area. Now, make sure, guys, do not attempt this at home. Okay, Reagan, we don't want you going off and trying to see if you can lay on a bed of nails or something. Wouldn't want you dying. Well, all right, so in attempting to do the bed of nails demonstration, would it be wise to begin with a few nails and work upward to more? Absolutely not. That would be... there'd be one less physics teacher. I'm sorry, but no, there'd be one less physics student because the physics teacher is a little smarter than that. All right, section 6 was talk about free fall. And we'll get back to Galileo. And if you were in our lit class, we've talked about this already. But if we talk about objects that fall, they accelerate equally due to gravity. So if I drop a 1 kilogram object out of a window and a 2 kilogram object, they're going to hit the ground at about the same time, and they would hit the ground at the same time if there weren't any air resistance. So if we were assuming there's no air resistance, they would hit at the same time. So here's Galileo. He's up dropping things off of the Leaning Tower of Pisa. And I think, I don't know, I think it's funny how earlier in the book they talked about how this really probably didn't happen, and now they showed this picture of him supposedly doing this. But whether he did it or did not do it, nobody really knows for sure. But the truth of the matter is, what they're trying to show you here is if you dropped a 1 kilogram object and a 10 kilogram object from that height, originally Aristotle said this one would fall 10 times faster than the 1 kilogram object. Well, obviously, that's not the way it works. When he did this, if he did it, they would have landed very close to each other at about the same time. Maybe a slight difference, but not 10 times different. It would have been 10 times faster. So this was a way to prove that objects fall at the same rate despite what their weight is. Doesn't really matter. Okay? Well, if we're talking about mass and weight, remember we're talking about on the Earth, they're proportional. So if we've got a 10 kilogram cannonball, you know, it's going to experience 10 times as much force. So you would think, oh man, that's going to accelerate that object 10 times as much as a 1 kilogram object, because that's what Newton's law says, F equals ma. So if I put in, you know, 10 kilograms, 10 meters per second squared for acceleration in that first one, I'm going to get 100 for my force in newtons. And the other one, 1 kilogram, 10 meters per second squared, 10 newtons. So it would look like, oh yeah, it's going to fall a whole lot faster. You got 10 times the force making this thing move. Okay? But you also have 10 times the mass. And in order to accelerate an object, according to Newton's second law, if this is bigger, it's going to take 10 times more force to accelerate that object. So here, even though I've got that force of 100 newtons, here I've got the mass of 10 kilograms. Over here, I've got the force of only 10 newtons, but I've only got the mass of 1 kilogram, so it's easy. It's the smaller object. I can accelerate it faster. Well, both of these end up being 10 for our acceleration. So despite the fact that one is heavier than the other, and it gets more force, it's applied, you know, the force of gravity is greater pulling that thing down, well, it takes more to get it going. So that's where it completely balances out. So in a perfect world, in that perfect air resistance-less world, they are exactly the same. And you can read that if you want. So both of these are going to fall with an acceleration equal to g, or 10 meters per second squared. Now, let's go on and talk about air resistance, because we know that obviously there's a difference. When we're talking about a feather and we drop that and we drop a coin, they do not fall at the same rate. Well, that's because of this wonderful thing called air resistance, which technically is simply just friction, fluid friction. Friction, yeah, that's right. Okay, so that slows down the one a lot more than the other one. So you experience more air resistance the faster you go. You know, if you hold your hand outside of a car that's going, you're going to feel a whole lot more than if you're just walking. And air resistance is directly proportional to the speed and your frontal area, you know, what surface area you've got facing into it. You know, obviously, if I'm a skydiver and I'm going down head first, you know, how they dive down there, I'm going to be able to go a lot faster because I don't have as much surface area versus when they lay out, you know. and they create a whole lot more surface area, frontal area in this example here. So then we reach this thing called terminal speed or terminal velocity. Well, that is the speed where the acceleration downward due to gravity is exactly balanced by good old friction. So here we've got gravity. This would be the force of gravity. Would be equal to our force of friction. And an object like a feather would get a lot more friction force on it, so it would hit terminal velocity a lot sooner than would an object like a coin. Now, it's important that you understand that just because we have zero acceleration does not mean that we have no velocity. You know, when the person comes out of the airplane and they pull the parachute, eventually they hit this terminal velocity. There's no acceleration, but they're still falling. They still fall, but they just don't accelerate and go faster and faster. That would be the bad part. You know, I mean, you can jump out of the airplane here and on the Earth and eventually land and be safe. You did the same thing on the moon, and you would just get going faster and faster and faster until you crashed into the Earth or crashed into the moon. Okay, so skydivers reach that terminal velocity or terminal speed when their air resistance equals their weight. Weight is a force. Air resistance is a force. A feather's going to reach it very quickly. Coin not so quickly. And if you're a heavier person, you're going to attain a greater terminal speed than a lighter person because for your surface area, you've got more mass than you add more in surface area when you do that. Okay? And body orientation, we talked about that. If you're leaning, going straight down, you're going to go a lot faster. A diver diving through the air straight down is going to go a lot faster. Okay? Than the squirrel who's got his, he's spread out and he's going to float and fly through there. Okay, and you can control your terminal speed. I mean, you've all seen movies where the skydiver, they dive, they go get the guy, they wrestle, they grab the parachute, whatever. And then they pull the parachute and save themselves. And, then they're going about 15 to 25 kilometers per hour, slow enough that you can hit and land and not get hurt. All right, at low speeds, air resistance, usually not a big deal. High speeds, a lot bigger deal. If you take a baseball and a tennis ball and you take them and you hold them right now and just stand out there and you drop them, they're going to pretty much hit at the same time. But if you go to the top of a building, let's say you went to the Empire State Building and drop them off, you're going to see a bigger difference because the faster it goes, the more this air resistance is going to build up on the tennis ball. Okay, so the baseball will be able to travel faster. Here's an example with a golf ball, and you can see how when, as it starts, they're pretty close. It's getting a little farther off now. We're getting farther off. And so because the golf ball actually has less air resistance than this, I don't know what they said, this styrofoam ball or whatever, then it's going to be able to fall faster simply because it has less air resistance. All right, which experiences greater air resistance force? A falling piece of paper or a falling elephant? Think carefully.